Okay, Gandhi.
Right. What? Good evening, everyone. My name is
Here you
Ian.
I can hear you.
All right. Yeah. Today, the topic that I'm going to explain or to present today is called Heisenberg's uncertainty principle, and it states that the more accurately we measure the velocity of a particle, the less accurately we can measure its position in space. To go to the inside, Heisenberg's uncertainty principle has this following formula, which is a delta x, which is uncertainty in position, times a delta p, an uncertainty in momentum. It should always be greater or equal to the Planck's constant over 4 pi, or as it is may be said, reduced Planck's constant over 2. Planck's constant, as we know, is the quantum or the minimum energy of an electromagnetic action that relates a photon's energy to its frequency. As we have seen maybe from previous formulas, h, so the Planck's constant h times the photon's frequency f, h times f is equal to E, or the photon's energy. And by this formula that we have on the screen here, it means that the more accurately you know the position, so the smaller this delta x becomes, this difference in x, then the less accurately you know the momentum. So the larger this delta p should be, so as not to break this law, this limitation. And vice versa is the same. It works the same. So let's imagine that we know exactly how fast a particle is moving or is going, but if we do, we cannot know where exactly that particle is, like this in the figure, for example. So we don't know where exactly that particle is in space. And according to the principle, that particle doesn't exist at all until we re-observe it. So as we focus on until we refocus on the position and we neglect the speed or the momentum. But does this make logic to you? Actually, when Heisenberg was at the beginning of doing this hypothesis, people were talking about him as he seems to be very certain about everything these days, they said. Imagine if you are, for example, in a train station and you see the following table over there, arrivals and departures. And it is written, this railroad is governed by Heisenberg's uncertainty principle. The location and speed of any given train cannot be specified for any given time. Now, let us pause a little bit at the nature of the objects. We know that uncertainty principle exists because everything in the universe behaves both as a particle and as a wave at the same time. Like this, so everything it is a particle and a wave at the same time. Particles, by definition, exist in a single place at any instant in time. Waves, on the other hand, are disturbances spread out in space, like this following graph and these following figures, of which we can identify features. And one of the main features that we need is the wavelength. The wavelength is the distance between two maximas, or two upper parts, with two minimas, or two shores up. Wavelength is essential for the quantum physics because with the wavelength we can measure, we can denote the momentum. What does this mean? Momentum, in the formula, it is mass times velocity. M times v is momentum, p. Now, from this, we can say that if an object is moving really fast, then it means that it has a high momentum, which results in a short wavelength. While at the same time, if an object has a high mass, it means that it has also a high momentum, and again, it results in a short wavelength. But since also the higher in mass objects have short wavelengths, this is the reason why we do not notice the everyday nature of the object. Because in the micro level, for example, if we throw a baseball up in the air, the wavelength would be very small to measure it, since it has also mass and it affects the momentum. And it is also impossible to measure it with our scaling devices. While in the quantum world, on the other hand, the atom has a lower mass, and it gives us more space to calculate the frequency and define the wavelength, so to calculate the velocity. And if we have a pure wave, we can measure the wavelength and momentum easily. more easy than in macro world. But what happens if we measure both the wavelength and the position at the same time, so as to break somehow this Heisenberg's uncertainty? What can we do is we add up waves. We have different waves with different frequencies, and we add them up all together. And we get something like this graph. So we have different waves at different frequencies. And as we can see, so in some moments in time, we have one wave has a maxima while the other wave has a minima. And when they will add up, they will create a stabilized point. While at some other parts, we have a maxima from the first wave and a maxima from the second wave. When they will add up together, they will create one distinguished peak. This following graph, I guess, it explains it better. So if we add up many waves, then we will achieve a graph like this, where we have stabilized lines, or how to say, probability that there might be no waves at all, and then there are some regions, like these three regions here in the graph, where it is a higher probability of having a wave and having an electron. And if we keep adding waves like this, we can have a wave packet, like this one here. We can imagine as a wave packet, which means that all the waves have a high probability of that we know the speed that they have in these wave packets, and we also know the position where they are. So both of them at the same time. So they create somehow clear waves in a quantum region. And that's a quantum object with both wave and position at the same time. So something like this. Adding more electrons, adding more waves, we have dense regions, and we say, yes, I know that here there is electron, and I can measure its speed or its frequency. So I can measure both of them at the same time. But we measure the probability of both of position and frequency, and we neglect the exact position and the exact frequency, or the exact velocity. Then another painting says that I know where we stand right now, Dr. Heisenberg, but where are we going? What does this mean for the macro world, perhaps? How do we use that? Some types of wave packets used in transmission signals are as follows, as it might come into interest as engineers. When we want to have narrow wave packets, then we have a delta P, which is large, which means we have a high frequency of the wave. And this results in a delta X, which is small, like this. While figure B says that if you want to transmit a wide wave for different modulation parts, you need the delta P, which is small, which means if the frequency is small and we have a longer wavelength, and results in a delta X, which is large, like this. Another example from everyday's life. The police stops someone in the street and she says, "You observed me speeding. Are you familiar with the Heisenberg's uncertainty principle?" As we said, if you measure the position at one time, you cannot measure the velocity at the same time too. So since the police saw her speeding, then it means that he shouldn't be able to see her position. And this is one of the questions that Albert Einstein arose or posed to the Heisenberg uncertainty principle, stating that if we consider everything being governed by the rules of the Heisenberg, it means that every car that is moving, for example, every object that is moving in the world, it means that if they have a velocity, then they do not have a position. And according to the law, they doesn't exist at all. But how to come to the earth and say why these things happen, why we see objects which have velocity and we can define their position? The example comes with the sun. The sun emits a light ray, and if we have a ball which is traveling in space, maybe Heisenberg says that we do not see the ball exactly since it has a velocity. We cannot say what it is, its position, but we rather have a reflection or the light ray that has bounced off the ball, or a reflection of the light ray which has been into the ball. And since we do not know the velocity of the light ray, we cannot measure it with our eyes, then we can know the position of the light ray and we can see what's happening here. We have a visual view. That's one interpretation. interpreting on that. And it defines a common sense that the rules which governs those things we can see do not apply to those we cannot. The quantum world with the Markov world still remain somehow divided from one another, and they have their contradictions, but some laws are able to be interpreted in both of these worlds or universes. I thank you for your attention, and I finish the presentation.
Okay, thank you, Gentil. Yes, you gave a presentation of what the Heisenberg uncertainty principle is, and this principle, in fact, it constrains the knowledge of two conjugate quantities. Okay, so these conjugate quantities, or how can I say, reciprocal quantities, they are the same or equivalent to what we said the last time. So last time we said that here we have some x, and here we had some k, okay, which we could also determine these as delta x and delta k, which were the, from this perspective, we can consider these like the error levels in determining the x and the k. And then we said that we could get a higher precision. We can get, so for example, in this case, if we have a particle, we don't know where the particle is. It can be from anywhere in this zone. Okay? But by increasing the resolution in x, we decrease the resolution in k, because this becomes 2 delta k. But this part, I believe we discussed this one from the last time. And it is always useful to use, to think about this principle, which is, and sometimes what is impressive is that it is always good to ask someone who does not have the complete understanding of the field, because they might have more imagination, or their imagination it's more free than someone that is used with a common terminology. What do I mean with this? An example is the following. So let's assume we have x is a parameter of a specific particle, and this delta p, this is mv, okay, mv. And this is again larger than h over 2, and this mv, we can also, you can also rewrite this one as mc. Okay, let's assume that c is the speed of light, which is 3 times 10 to the power 9, and this is the x. Now there is this term here, and regarding this, we can assign, how can I say, let's assume this delta x can be assigned for any particle which is like this mv. So the linear momentum is here mv, but we can also decide this one as mc. And what is interesting is that, well, this quantity, this shows that, for example, if you are dealing for an electron, which is a small particle, for an electron, this delta x is something in the order of 10 to the power minus 15. Okay? If we have a truck, or let's say if we have 1 kilogram, we can have a delta x which is in the order of 10 to the power minus 20, sorry, no more, let's say minus 30 meters. So if these fluctuations, or if these uncertainties in determining the exact location of a certain particle is large, then we can say that here quantum effects are large. Okay, quantum effects are large, but if the uncertainty in determining the position of some particle, then we say that quantum. So here quantum effects are large, and here we can say that the quantum effects are small. Okay, and what is interesting is that we have two completely different domains. So let's try to represent something similar here. And now this delta k is this parameter mc. Okay, mc, which is because this is the reciprocal space. So you can see here, this you can also see this one delta x, delta k is larger than h over 2. And last time we said that minus ikx, this is a parameter which the students in electronics engineering have seen this a lot. So they see it like this. but at the same time, anyone in mathematics, if you see the Fourier transform, we have said before, the transformation from X domain to the frequency domain is expressed by this kernel, dx. Okay. So this term, so I'm just saying this one, that we can argue that these are somewhat equivalent. And now, in terms of the real world that we measure, there is, let me say it this way. So I'll try to explain in 2 to 3 minutes what I want to say. So imagine now that here you have an electron, okay? This electron, and how can we increase? Let's say, so this is small. How can we increase the term mc of the electron? This is 10 to the power minus 31 times 10 to the power minus plus 8. This is the speed of light. This is for the electron. We're talking about 10 to the power minus 23. So how can we increase this? By increasing, by increasing the mass. Now we have another domain which is for the heavy objects, and for heavy objects, let's assume an object of 10 to the power 30, which is the mass of the sun. Now this mc. So let's actually, I think I can try to clarify this one. So what is the mc if we are talking about the star of our solar system? If we have the sun, this mc or this mv here, this is going to be something like 10 to the power 38, right? If this is 10 to the power 38, how can we increase this quantity? Actually, we cannot increase this quantity. How can I say that? Based on the numbers that we see here, this means that for heavy objects, we are here. This is 10 to the power 38. And all we can do for something which is like the sun, which is a very heavy object, even us, a certain individual or a person that has a mass of 70 kilograms or 80 kilograms, once we calculate the mc of this individual, we are up here. So we are drawing something equivalent. So this is the electron. Electron, it starts from here. Probably I want to draw them right in this space. So this is the electron. Let's put here the sun. Now the sun, the mc parameter, this is 10 to the power 38. So this means that we are here, and all we can do is trying to with the second. So this is large, and this is small. We are making this large. So if this is large, how can we make this smaller? How can we come down? Okay, this is a fundamental question. And there is a trick to do this. If in this expression, if for the electron, we use this delta x times mv, here we have to use delta x times 1 over mv. Okay, this is something very impressive, which should be this way for several reasons which we could argue. The units don't match. Okay, so if we here the units for the electron, they do match, because we know that this one times this is the units of the Planck's constant. This does not have the units, but the value should be the same. And somewhere in between, if we increase the mass of the electron, which means that we can find some mass where this should be the other way around. So again, we have an inversion here, but somewhere in between, we have something which is called the Planck's mass. The Planck's mass. And this constant h, this was the Planck's constant also. So this was the Planck's constant. Let's put this. And this is the LP. And this quantity, the Planck's mass, is the quantity which is mc, it's equal to 1. Okay. So for objects that are lighter than the Planck's mass, we have a regime where we start the analysis, or we can call it also this way, the way that we conduct the measurements for objects that are smaller than some critical mass, which is the massageplankton, als masskritieken. They have a specific way how they behave. So we start from an MC, then we go up by increasing the resolution in here, in this axis, but by losing some resolution in this domain. With these objects, with heavier objects, they do something different. Okay, so we use such a parameter. And what is interesting is that one can obtain different forces, but this is out of the scope of the topic for the course. But if anyone is interested, we can discuss after the class, especially this specific aspect. So you can also link different forces of based on these principles. Okay, but this is really something which would be out of the scope, complete scope of this course. But in terms of this analysis of the resolutions that we are talking about, we can look at an example here. So what we can do, let me have a look. Okay. So just to show how, let me do this. Okay, so let's try to compose. So first of all, let's try to compose, wait a second. Let's assign some value over which is going to be in the time domain, and we set this one L is equal to 10. Then we can also determine the number of Fourier modes, which we can, which means that these will be the number of modes or the number of discretization levels. This is how often we are going to get discrete points. So we assign here T2 is Lin space, and what this Lin space is doing is counting some values in time from 0 up to 10, equally spaced from each other. So here we assign, it's critical here, because at this point we have n+1 number of points and n+1 points, but here we have just 10 points, and here we get T. Then here we prepare also the other domain, which is the Fourier domain. So we prepare the K, and here we can make up a function, which is a composition of sines, tangents, exponentials, sine again with a different frequency. So all of these numbers we can change these. So we have here the sine of a 2 times x. And by the way, I wonder if I can increase the size view. That's right. No, I cannot do this. Okay. I was just wondering how I can increase the size of what you see on the screen. I used to know it. I don't remember how I do it generally. Okay. So anyway, so we have the time. So the time that we have set, these are the times. Okay. So let's see what they are. So they go from 0 to 9.9951. Apparently that's the last increment. And we can also generate this function S, which is composed of sines and sines, exponential, inverse tangents. So let's see what we get here if we plot S and as a function of time. So apparently this is our function. And for this specific function, this is what we get. And we see that this function at specific, at the low time, at an earlier times, which is the time from 0 to 3 seconds, or whatever the unit is, we see that we have a higher frequency components. But somewhere between, let's say, between 3 and 6, we have smaller frequency component, lower frequency components, because this is time, okay? And something somewhat between 5 and 8, we have much lower frequency components because the period of these peaks is smaller. So the peak, the distance in time between two subsequent peaks, which would be like a periodic behavior, it is larger, that means the frequency is lower. So this is our function. And this function S, which is a function of time, we can generate, so we can get the FFT, which is the Fourier transform, and this is just a function y as a function of x. We just need to use the fast Fourier transform FFT, and here we assign a specific width, which we better set here equal to 2, and so this width equal to 2 is the window over which we want to analyze the frequencies in one section. So in fact, what we want to do here is that we will conduct Fourier transform, but we are going to conduct a short window Fourier transform. So this part we can do also short window Fourier transform, and we can denote this one as SWFT. So we don't want to conduct the Fourier transform from 0 to 10, which is the complete time, but we want to, so we don't want to calculate the fast Fourier transform from 0 to 10, but we want to do it, let's say from 0 to 2, and a little, sorry, this 0 to 2, and then we want to calculate it again from 0.1 to 2.1, okay? Then we calculate it a little later, 0.2 to 2.2, and as we calculate all of these, we want to construct a sliding function or a sliding window over the complete function that we have shown here. So if we set width equal to 2, the slide is going to be from 0 to 10 with steps of 0.1. Okay, so we define this variable here spec, and this says from j it should go from 1 to length of the slide. So slide itself, let's see what is the length of the slide. It's 1 by 101. So apparently we're going to run this loop for 101 iterations, and sorry, let me see just no. Sorry. So we just want to do this short window Fourier transform at specific windows, and if we see this, so here we have a function f, which we can set this one. So width is equal to 2, t is equal to minus slide j. The first slide is what? J1. It's wait a second, length slide. So this is actually just a Gaussian. Okay, so what you see here is a Gaussian with a specific amplitude and width. And let's say we said that this is centered at 4. Why did I say this one time? No, it's not equal. Maybe this is not correct, this comment here. But once we conduct this window is in the real domain. Okay, so the axis here is time. Then what we do, this function that we have that we see here on this plot, we multiply it with this specific function f. So actually we know the width is 2. Let's set this one. What is the slide j? So if j is equal to 1, wait a second, slide is going to be 0. So this will be, actually let's set slide 2. If we call this one slide equal, or let's call it slides equal to 3. If slides is equal to 3, then we can compose a function which is, let's call it slides. The width, it's a given function, and let's do it like this, and we can have here figure 2 plot TF. So this is the figure 2, and as we can see, it's simply a 0 to 1 gate, but it's not 0 to 1 gate exactly. It's like a Gaussian which offers smooth changes from 0 to 1, and this is necessary because when we take the Fourier transform, if we have a function which is not differentiable, we get a lot of distraction or deformation of the signal. So if we see here, we have this gate of 1, which if we set this one on top of the 3, this is going to and is going to multiply with 0 anything smaller than 2 and anything larger than 5. So once this function in figure 2 is multiplied with this function in figure 1, we're going to have, as we said, a function limited in the window, which is different from 0. And this function, which is limited, is wait a second, it's here. So SF is a function 0 at some domains where we have set it. Here we take the Fourier transform. In fact, we have S and F. So let me call this one SQ is equal to S or F times S SQ. Okay, so this is what we so most probably it's already clear, but by multiplying this figure here with this gate function or with this Gaussian centered at 3, all we're going to get this region. Okay, so then once we get this signal in figure 3, then we calculate the Fourier transform of this patch or of this little piece in line 17. Once we do it, we try to plot it, and we want to plot the original signal, which is S. So we want to show this. Okay. Then we want to show also what is the window over which we are going to calculate the Fourier transform. So we plot also the SF, which SF in this case would be this. And after we plot the SF, we want to plot also the Fourier transform of this SF, because those, we find them here. So this is actually this is not, we cannot call this filtered. This is not a filtered function signal, but it's just a signal which is made 0 in the regions that we don't want to analyze. So this is what we can do here, or this is at least what this is doing. And let's do it like this. So here we can see the original signal on the top. Then the red line, which is sliding, is in fact the filter, the gate function. And then the product of these two graphs here on the top, I think maybe it's clear. So this is the spectrogram. So all we see here is in fact so this figure 2 is in fact the schematics that we do where we say that the smaller the delta K, the larger the delta X, or the other way around. So again, if we see here, the magenta color or the red color times the original function, which is given here, those are multiplied, they are shown in the second graph, and then we get the Fourier transform in the third drawing. Now we can have a look at this, and wait a second. Okay. So this is the spectrogram, and it is good to notice actually where is the x-axis. The x-axis is on the horizontal axis, which goes from 0 to 10, and the y-axis is from -60 to +60. So this is how where this one is going to be projected. And let's see what happens if we change this width. So now it is 2. We can make this one 0.2, and with this operation, if we change the width to 0.2, that means that we're going to have a very good localization of the signal in the x domain, but we're going to lose the resolution in the k domain. So let's see how we can visualize this in here. Yeah. Wait a second. We set the width 0.2. No, I was wrong. I said the opposite then. I was completely wrong. But we can correct ourselves. So wait a second. So in fact, when you see here, it's exactly the opposite that I just said before a while. Why is that? Because we see that as we move in the horizontal axis from x2 to x equal to 4, we see a very gradual change of the intensity. So we don't have very good resolution. But on the other side, if you look for the vertical component, we have a very good, very nice resolution. So we can easily distinguish where, if we see this region here, wait a second. So if we try to focus here, so it's a little more clear. So the resolution, it is defined as we're moving over a vertical line, we notice that we can easily distinguish where is the boundary between a darker region and a brighter region, which is can be seen in here. But this one is much more difficult for the x-axis. But now let's see this width. Let's copy this one. I'll try to copy this. Okay. Okay, then let's have a look again at the code. We decrease the W, the width. So the width decreased from 2 to 0.2. Where does the width appear in the equation? So here we have the width. Wait a second. This is exponential minus the width. But this width is, okay, we decrease the width, but t minus t slide. Now the width, okay, we made this one 0.2, but this was the amplitude. T minus slide. T minus slide. Wait a second. I cannot see. So the filter is in the real domain. We made the width e to the power x squared. Okay. Okay, now I see this. Actually, the width, so, yeah. Now I understand. Normally, the Gaussian functions, probably you got this one before me, but the exponential or the Gaussian are always described like this. Exponential to the power x minus x0 all squared divided by 2 sigma squared, okay? So this is what the sigma is, and in fact, this width, for a moment I was confused, okay? So this t minus slide j, 2 square, this is this part of the Gaussian, okay? So this identifies where we're centering. This is a changing variable this is fixed, and this 2 sigma square, in the previous case, this width for us, at least maybe for a couple of minutes, so that we record. Wait a second. You are presenting. Stop presenting. Anyway, so I think that I'm clear myself. But this width, before a moment, this was equal to 2, and the second case, we make this one 0.2. But this equal to 2, this is multiplying this, which is equal to 1 over 2 sigma squared. So the width of this Gaussian, this means that this is equal to what? The sigma here, this is equal to 2. So if this is the case, what is sigma? This looks like sigma is equal to, so let's get the sigma here, 1 over 4. 1 over the square root of 4, which makes this 1 over 2. Okay, so this is 0.5. Okay, now I get it better. But at the same time, this is 2 sigma squared, and here this 0.2 is 2 over 10. So we have here 2 over 10, and the sigma squared, this is equal to.
That will be covered.
10 divided, yeah, is it true? So 10 over 4. So sigma itself is square root of 5 over 2. So it's 2.5. The square root of 2.5 is 0.05. 0.05? No, that's wrong. 2.5. Actually, let's do it better this way.
Is it a start, professor?
It's a start?
Oh.
Okay, thanks. Yeah, okay, so this is the sigma. So apparently, the sigma, or the width of the function, it has is opposite what I initially said, because I missed this part. I thought we were dividing the Gaussian. I thought the width was shown here, but apparently the way we've written it, the width of the function, it goes from 0.5, which if we have here 1, 2, 3, and more, and 4, the initial width was 0.5, so this would be 0.5 would be this width. So this is 0.5, and since this could be one of the few courses which you're going to see this content or this material, I hope you learn from here. You learn it in this class, and then here the sigma, which is 1.27. We take 3 minus 1.27. This is going to be 1. This is like quarter. So at this line, we get this. 3 plus 1.27. So this is 1.3. This is 2.7, right? Or 1.7. This is at 1.7. Around 1.7. Here, we're going to get 3.3. No, 4.3. So this will be the, wait a second, okay. So from the center here, this width, which is equal to this, which is equal to this, maybe the drawing is not to scale, this is 1.27. And you can even double check this on your own. I'm going to share this this code with you also. But it looks like now we understood this. But I hope we also got a review of how we represent the Gaussian function. Share the entire screen. And okay, so we got this part, and it looks like by going down by decreasing the width, we were, okay, so decrease width from 2 to 0.2, but when this was 2, the real width was 0.5. So this was 0.5, and this width is 0.2. That meant this was 1.27. 1.27, which means that we have kind of multiplied by 3, almost, or no, 2.5, 2 point something. 2.5. So we have multiplied 2.5 times more. So with this operation, what we have done is that we have really decreased the sigma Now wait a second. So we decrease from 2 to 0.2. So in this case, we have made the width of the Gaussian 1.7. So we have lost resolution. Yes, and this is what we observed. So we lost resolution in the x-axis, but we increased the resolution indirectly because the delta x now is smaller, sorry, is larger, but the delta k is smaller. Okay, so we made this 0.2. I believe now we can also change this variable. We can even set this one. I don't know what we get if we set this one 0.05. And if we run this function, so we see that the resolution in the x space, it's very bad because this width of the function is taking the Fourier transform of the whole function. Okay, it's not really taking away any component. And at the meantime, you can also see that the third graph here at the bottom is not changing. Okay, so this one, it never changed. So we could see in the previous cases, we could see the third graph down here changing, but now it's not because it did not affect much. But if we see here, we really have a very good, okay, actually this is a good example because we see that we don't even know where the signal is coming from which, so we don't know this frequency, which is very bright. Very bright means that in the y-axis, it's something, a value between 200 and 250. This value, we cannot distinguish where it is coming from which value of x it is really coming. But if we see here, so if you see this, this graph here, which is, now we have this on the PowerPoint, we can really determine that this, I believe you can see my mouse here. Maybe it's good if I add some components, which could be like a rectangle. So here, this is where we can localize where this specific frequency is coming from. This specific frequency is coming from a time, something like between 2 and 3, okay? But when you see here, the resolution is much worse, okay? So it's almost very difficult to determine, and I think we try to make it clear why this is the case. And okay, something else we can try this. I'm not sure if it's on. Now with this very high resolution in this, we set this one too small, the width 0.05. We can try to set this one 5. But if we make this 5, this was inverse proportional to the resolution in the x-axis, and probably this is going to be the last time we run this. And let's see what we get. So you can see how fast the frequency components are changing here in the third function below. So once we go here to this region around 6, we just have very low frequencies. So we have frequencies which are between -10 and +10. But once we go here in the region of 9 and 10, we have frequency components that extend down to -20, +20. Okay, and this is what we see. So we increase the resolution in the x spaces, but we lost it on the other domain. This is what Genti was trying to explain when he talked about the Heisenberg uncertainty principle. It's a principle we started from physics, but it clearly reflects itself also in the signals. And actually, this is not something to be surprised. I mean, this is how it goes. And all the beauty actually which is hidden between all of this nice discussion that we are having, I personally consider that this is all as a derivative, or we can see these nice representations only because we have the complex numbers. Okay, because if we did not have the complex numbers, if we did not actually complex numbers, it's a mathematical tool or apparatus that can help us to understand the phase. Про фаза не надут numeri complex. Про фаза как existuar, so the phase, it's always there. We can always assume we have two waves that they don't reach the maximum at the same time. Okay, that's phase how we understand without the need to have the complex numbers. But in order to conduct all these operations, we need to have these complex numbers, which they do reflect themselves when we take the Fourier transform of specific signal. Now, so far, we started the Fourier transform, which was the decomposition of a signal with respect to sines and cosines, and the principles we started it from Fourier Fourier series expansion. And now, but Fourier transform, it was for periodic functions, a function which repeats itself continuously. And now we just saw what is a short window Fourier transform. So it is a localized in a narrow x in the x-axis. If we have some specific resolution, that one is going to reflect itself in the reciprocal resolution in the k space. So in this case, the x and the k, or the x and the y axis, which are shown here, we can call them reciprocal spaces or conjugate spaces. Okay, so there are spaces which or orthogonal spaces. They are not exactly orthogonal. They are not perpendicular with respect to each other because that would be x and y, and these belong to completely different. How can I say it? Different domains. So they are not orthogonal. They will be orthogonal if they are in the same plane. This is the same way, like maybe this could be a comparison, which we know this from 6th grade. When you were 12 years old, we had to learn the definition of parallel lines. So two parallel lines are not two lines that don't intersect with each other, but there are two lines which are on the same plane and don't intersect with each other. So this makes them parallel. With the same perspective, we cannot define actually the complete orthogonal directions for two different components if they are not in the same domain. So one is in the complex space, the other one is in the real space, but we don't call it orthogonal, we'd better call them conjugate and reciprocal. So now these waves, so we decompose the signal on sines and cosines, so using sinusoidal function and cosine function. Now the similar task, we can do it also using wavelet transform. Now, wavelet transform, they are wavelets which they are useful because sine and cosine, if we use those, so what happens is the following. So sine and cosine, they are not localized at all. Okay, so they go, if you draw the sine of x, it's from -infinity to +infinity. Okay, so that's what sine and cosine is. So it's not located in x space. Now, what mathematicians have developed is the following. So they say that let's use wavelets which are localized. So whatever, probably at this stage we could stop presenting the screen. So we started with Fourier transform, sine and cosine. So these two components, they are not localized in the x-axis, but they provide very good, very high resolution in the frequency space when we measure the hertz. And this one, so we do the Fourier transform. This is delta x is bad, so let's call it it's large, and this means it's bad because this means that this is low resolution. So these three concepts, they are equivalent when delta x is increasing. Then with the short window of Fourier transform, we got the delta x it decreased because we were taking the Fourier transform over one localized space, and this is better. I mean, better because we have high resolution in x space, okay, in x-axis. Let me call this one in the x-axis. Now, since the k-axis is, so this means low resolution in x, but at the same time, probably it's better if we write it like this. Low resolution in x space, but we have high resolution in the frequency domain, in the k space, so let's call it k and x. So by making the resolution, high resolution in x-axis, we can make a lower resolution in k space, k-axis.
So short window, I refer to real space or Fourier space?
Cila?
Short window, the termi, pra do të me kanë delta x e vogla o i madhe?
Jo, short window është në real space.
Në real space, a?
Po, pra ne po integrojmë në dritare kohore të vogël. So even the example that shembulli që pamë pak më parë, ai që bënim ne është që ne shumëzonim gjithë funksionet që ndryshonte nga 0 deri te 10, ne e shumëzonim me një dritare të kohore të ngushtë midis 4-s dhe 5-s, e shumëzojmë aty dhe pastaj po merrni Fourier transform. Po në momentin që ndodh kjo, kjo direkt na sjell sepse kjo është lidhur me njëra tjetrën, po nuk kanë indikatër. Nuk kanë indikatër se vetim të data x data k. Kjo gjithmonë një constraint, dhe është interesante fakt se ndonjëherë dikush mund të mendojë në këtë formë. Thotë, pse do të jenë kaq lidhur me njëra tjetrën? Se në realitet edhe mund të jenë. Në realitet edhe mund të jenë kështu, mund të hahen me njëra tjetrën se kush which one is going to compete with respect to each other. Dhe ti mund të thosh, por të paktën në aparatin matematikor kjo duhet të reflektohet, por reflektohet. Pra kjo humbja e rezolucionit është gjë shumë e bukur e panditshme sepse this one is reflected even in the mathematical apparatus, which in principle it does get close to the reality, probably because we don't have division by zero. Okay? In mathematics, it is not that we are given the opportunity to get close to singularities. Okay? To get close to singularity, from one perspective, we can assume as if you are dividing by zero, and we can continue. So because they are strongly related, we get this. Now, whatever is done by using Fourier transform and short window Fourier transform, mathematicians or signal processing researchers, they've developed another transform which is called the wavelet transform. And the wavelet transform is in principle trying, in one way to think about it, is trying to mimic what the short window Fourier transform is doing. And we have developed some wavelets which, so for example, this is a very common wavelet. This is called Mexican head wavelet. This is how they call it. So Mexican head. Wavelet. And wavelet, this just means that this is a small wave. Okay, so we are defining a small wave, not a sinusoidal wave which goes from plus infinity to minus infinity. But it's something which is somehow analyzed as shown in here. And other than, for example, other wavelets, one traditional one is Dalbech's. I mean, the spelling of this one, it's a little challenging for us to spell it. It's the last name of the mathematicians who developed it. It's a very common wavelet which is used. So this is called the Dalbech's wavelet. In programming languages, now they are easily implemented. You don't need to write the function, but it's always good to check what the function looks like. Okay, so Dalbech's wave, and you can. The idea is that at different locations along the x-axis, you can have higher amplitudes so that you can pick up lower or higher frequencies. I've looked of course I've looked at many times, but if you have a look also, like me, at the shape of the Dalbech's wavelet, you can really, you can use a little bit of intuition to derive or to deduce that this specific wavelet is useful because it has this frequency component which is located here and there. So you can, you get this insight from this course material. So this would be Dalbech's wavelet. When it comes to the programming languages, all you need to do is this, DB. DB is Dalbech's. Or sometimes you just say DB2. DB2, which means that this is for signals in two-dimensional signals. DB is for signals as a function of time or as a function of x. This is all you need to do. Now, we have also something else, which is the following. So, in Fourier transform, we used to have the sine and cosine in the. So let me do it here. So we used to have here an sine nx, okay, and n was going from 1 to infinity. Now, of course, we have an an. That coefficient an is always there, but in order to remember some of the concepts we have covered, this an is most of the time something like n to the power m, or that we write this one over n squared. Sometimes it's 1 over n, but let's write it like this because this reminds us that as n is increasing, the amplitude is going to decrease, so it's going to contribute less to the overall signal. So at high frequencies, we need just little bit of amplitudes to make up for hard edges where a function is not differentiable. So if a function is not differentiable or derivative is not defined, then we need high frequency components, okay? So always, if you are, whenever you have an edge, let's say that, for example, let's assume a case from images. So if you have an object that is located somewhere here, and this one is in black, we might have the intensity across this image. It can be gradual, so you can have a gradual change of intensity. But here, right at the edge, we have high frequency terms, because high frequency terms, they are responsible for this. Okay? High frequency terms, they are responsible for a change, a drastic change, from a very low value to a very high value. And so the edge, so here we have high frequency terms all in this boundary. In other regions, we have lower frequency terms. So, which means that if we want to figure out, where the edge of certain objects, or where the gradient is the largest, then what one has to do, we have to apply a high pass filter, which allows to pass only the high frequency terms, which means that we are going to lose some small changes, gradual changes around here, but we are going to enhance whatever is happening at these edges. Now let's come back to this discussion. From here, we can also see that as n is increasing, we are decreasing the amplitude, but we are also increasing the frequency. Now, something equivalent is also happening with wavelets, and with wavelets, what can happen is that we can decrease the amplitude, and this becomes like more like this. So they follow better in an equivalent way with whatever we have seen in the sine and cosine. So this is how the wavelets are changing, and yeah. And we have also the mathematical apparatus, which describes how the amplitude and the distribution, or the distribution of these wavelets look like. They are not difficult. The mathematical apparatus is not difficult. I strongly suggest you to look this one from the textbook that we share for this class, because they are very well explained, and they have several properties which we could go over those, about the properties of the wavelets, and I mean we can. It's always good to have a look, because they also give extra insight, which you can always make, which will always be useful, even when you are working not only with wavelets but also with sines and cosines. And the intuition the wavelets provide is always to many, it's assumed to be better than the intuition given by sine and cosine. So yeah, this was this is what the wavelets can be used for. And in principle, so actually the example that we saw before a while, we noticed that the frequency components, when you take the Fourier transform, they are located with respect to the zero. They are always a Fourier transform of any time scale, going from 0 to 10 or 0 to 100. The Fourier transform will always have a 0 here, and you will have plus 60 frequency component, minus 60 frequency component. And regarding this, always it's always interesting to provide some equivalent concepts which appear here and then, here and there to some degree. And actually, these ideas that we are discussing here, they could become useful, or they can support anyone who wants to understand a little bit more about quantum computing. Recently, in the last week at least, I've read like at least two or three different news where they report the use of quantum computers to conduct computations which takes years, and they have been done in a few minutes. And this afternoon, I also read some news where some supercomputer, quantum computing, in a research center in China, they had achieved, or they reported, the fastest computing unit, let's call it this way. So maybe we won't talk about this one during the whole semester, but one other intuition, or one very impressive aspect, which who knows if it's going to be true, sometimes we don't always have the proof, is the following. So often the nature, or which works in strange ways, that sometimes they do have the mathematical representation, but the mathematical representation, it could be represented in a way which we edhe nuk e pranojmë. Ne ndoshta se pranojmë fare, por kush e di, ai mund të jetë e vërtetë. Shembull për këtë mund të japim për shembull, dikur dim që probabiliteti është vlerë pozitive, pra për gjetur një grimc diku, probabiliteti mund të jetë 70%. Po ka raste kur probabiliteti mund dalë dhe negativ. Normalisht s'ka shumë logjik, por thamë që dakord, janë ca grimca që kanë probabilitet negativ. Më vonë eksperimentalisht u vëzhguan ato dhe doli që këto ishin pozitrone. Pozitronet, nëse besoj shumë disa përmesh në takim këtë, është që sikur kemi elektronin, kanë gjithë ato parametrat e elektronit, që kanë ngarkesën -1, pozitroni është shkruar me për dhe ka ngarkesën +1. Tani, pse po e përmendim këtë këtu? Përpara se përmend çfarë është arsyeja pse përmendim këtë moment, we said that we had this, okay, I can give the example of one respected physicist who said the following, because he said that how is it possible that the charge of the electron is so quantized? Pse është kuantizuar kaq bukur? Është e pamundur. Normally it's very hard to believe why all the electrons have a charge of 1.619 and 10 to the power minus 19. So there is a unit charge, and always this is quantized. No one has ever observed the charge, which is like 1.5 times the charge of the electron. And what Wheeler said was a very good, who was the professor of one of the Nobel Prize winners in physics last year. He said that, and he told this one to Feynman. Feynman was also a very good physicist. He said, you know what, probably all the electrons that we see in our experiment, it's only one electron. It is impossible for nature, he said, to produce electrons all so uniform. It should be only one electron, which is all out there, okay? So if we have, so the electrons could be, and we have electrons and positrons, we used to think like this. If you have a car moving in this direction, when it comes back, so if you move like this, when it is moving this way, you observe the same electron here and here. But then, when it's moving backwards, it becomes a positron. This is something which respected scientists, after they have achieved their fame, they can say anything. Okay? Nobody is going to blame them. But for other individuals, like some of us here in this class, we cannot express everything, okay? Because we might be misjudged. But one thing which could be represented as the mathematical construct of the mathematical tool of the electron, the positron, it could be the Fourier transform of the forces that we have in the real domain. They might represent themselves the same way that the Fourier transform represents each time we take the Fourier transform. We get the k-space, which is 0 plus this way, minus this way. This is always the case. Probably these two quantities, maybe they are the Fourier transforms of some measurements which could be constructed from the tools that we mentioned before a while. Okay? This is not simply just such a wild dream, what I said here. I have there are quite a few more arguments that we can say, but I doubt anyone has ever written this in a book, or maybe you might never hear this one in any other setting. But this is something which can keep us our mind open to try to represent, not to represent, try to explain what we measure in reality and how the mathematical tools or mathematical apparatus can help us to visualize or to make use of it. But I've never seen it anyway where the Fourier transform would explicitly report such a figure. But you might think about this one. Maybe the intuition might help you to develop some more interesting ideas. Now, let's skip this part. And so we said that this is the intuition which comes from the Fourier transforms. This is always the case. And this is not only for signals. This happens also for two-dimensional and three-dimensional examples, where the Fourier transform in 2D, it will just keep the zero in the center, and you might assume something like this. So once you take the Fourier transform of a 2D material, you always have a zero here, and all the frequencies they are equally localized all around. So this is plus kx, this is plus ky, plus, and this here we have minus kx, and this would be the minus ky. Okay, and then yes. So this was the Fourier transform. We said that we have the wavelength transforms, and then why did I start this discussion? I started this discussion because you might, whenever we see some examples, we're going to see that when you take the Fourier transform, now we know how they look like. We're going to see also the examples from 2D or mainly from images. But it's interesting, how does the wavelength transforms look like in the, not in the K space, but let's call it in the wavelength space. How does the wavelength transform look like in wavelength space? We call this one K space. Okay. Now, how was this? This was a series of coefficients which were located from minus 60 to plus 60. If the highest frequency in a specific signal is 60 Hertz. But now, the wavelength transform here, it does not have the symmetry with respect to zero like the Fourier transform, but it's going to have all the coefficients that we're going to obtain. There are signals which are going to look like this. Okay. Now, why do I show it like this? In principle, the low frequency components of the key element of frequency, we can use it equivalently in Fourier transform and in the wavelength transform. And probably we can say that the major difference is this, that these are centered around the zero. It's always the case. We always have in any signal, we always have a very dominant low frequency component. And then we have also very little, not very little, it depends on how the signal is changing. We might have less components in the high frequency domain. Now, last time, I think in the exercises we solved, we got a signal which was I think a sinusoidal one, and then we took the Fourier transform and we modified, if you remember from the previous session, we modified just one or two components, one or two coefficients out of 512. So we had 512 coefficients, which was the projections on different frequencies. We just modified one or two, and the signal, when we took the Fourier transform backwards, it was lost, or it had lost all its features. Why is this? Because we changed the low frequency components. So traditionally, unless we have noise, so noise would be something like this. Like the noise which you measure with an oscilloscope, which could be the noise that the signal picks up from all the signals and from the cell phones. If you get a piece of wire, or you get a piece of wire, you just hang it out, this becomes like a radio, and you move it around, all it's going to pick up, it's a lot of noises. That one, you put it in a BNC connector, you plug it into an oscilloscope, you're going to see just noise, nothing structural. Okay. If it is an image, the noise is going to look like this. White dots. Like when I was in the daycare, before I went to first grade, when I was 5 years old, I remember that the best drawing I could do, it was the rain, okay? Teacher was saying, what are you going to draw now? I said, I'm going to draw the rain. And the rain is this. And then this one, this is the only signal, or the only component, which has high frequency terms, which is not going to be affected. If you zero out, if you multiply, so let's say that you have a signal, and you have it in the Fourier domain, you multiply it with a function which is 1 everywhere and 0 here. The picture of rain, you are not going to affect it. You are not going to change because this does not have any low frequency components, unless there is a tree somewhere, and the rain is around here, by erasing the low frequency components like this, by applying the filter, you might remove the tree completely, but the rain is still there. Why? Because it's just pure noise. Now, so again, this feature of having the the low frequency terms around zero, this is preserved in wavelet transforms. It's going to look like this. Low frequency components have high amplitude, then they become smaller and smaller. And depending on the number of the coefficients, what happens is that we might get some components are very small. Actually, we're going to show very good examples once we go to the signals in two-dimensional signals. And most of the applications that we're going to see this semester, they will be on images. Not only images, but those, they do provide a lot of insight, and I hope you're going to see you're going to like them, because we're going to check how the Fourier domain is being affected by or how we can carefully read all the frequencies which are even at farther values of k. So they are not exactly zero, and we cannot really make them zero because we can never get an infinite precision. But these are something like 10 to the power, 10 to the power minus 17 or 10 to the power minus 16. This would be the coefficients, both in the Fourier transform and in the Wavelet transform around here. Now, what can be done is the following. So if we want to remove some noise from a data set, what one can do is that we can take the signal. Let's consider this one f of x. Okay? F of x, this is, let's say, f of x plus noise. This will have some noise. And this component, we can take the Fourier transform, we can apply ft, okay? We apply this operator, this ft, and then actually, I think a few examples we gave them last. No, wait a second. I think we gave this example last time where we applied the filter, which was centered around the zero. So we take the Fourier transform, and here we multiply with the filter, which is in the k space. So this is k. In the k space, we multiply with the filter, which is 0 and 1. And here we have filtered out the high frequency terms. The same way is done in the wavelet transforms in WT. So we look at these components. So the output is just this, and we multiply this output with a filter like this, but now the filter is in real domain. Okay, so, or we just zero these terms out here. An example, we can see, I'm not sure if I have the PowerPoint here. In fact, for next time, this will be like a homework. I'm going to post this also on Google Classroom. So you can get a signal or an image or anything that you want. You add noise to this signal and try to clear out the noise using both Fourier transform and the wavelet transform. Okay. Let me share this here. Let's see. Oh, what should I look at? Sorry. Okay. Let's see. Let's see what image I have here. So if we have a look here, let's evaluate, let's see one image that I can find here. Okay, we have Agron Lakai. And this image, it's in the variable, but actually before we do that, we have few variables here, all of these variables here. Maybe we should close all. Here all. Now we read that image. Let's do this again. Sometimes I figure it out like this. So these variables, they are all unsigned integer 8, uint 8. And in order to conduct some of the decompositions, the variables, they should be double, okay? Because they should be double because, of course, the output is not going to be an integer, okay? So once we do this double, wait a second, this is, we have, okay. One other thing that we can do here is that this image, it's a three-dimensional layer. It's 309 by 500 by 3. And this is figure 1, where we show the image A. We can also have a look how does figure 2 look if we do in show A. But out of this matrix A, we show all the rows, all columns, just the first layer. So let's do it like this. So we get, actually this is a black and white image, but this is composed of 3 different layers, the red, green, and the blue. And apparently we did not show much. Actually, we can pick another image to look at. Wait a second. No, these images are huge. I don't want to use those. Could read this again? No? Okay. So we have this other image, which is this this new variable, which is also 500 by, and if you want to see how all of these layers look like, so we have figure 2 is just the red layer, red component of the original image. Then we have the figure 2, this is figure 3, which is the green, and the last one is the blue. It's interesting that the blue is completely dark. How is it possible? We can also check the following. We can do sum, it should not be 0, sum of the matrix A, but in the matrix A, we want to collect red, green, blue. The third layer, it's a lot of material actually. Not material, but the pixel values are huge. But this is, anyway, so this is A1 is equal to this. Now, what I'm trying to do right now, it's something A1 and A2. We can do A2 divided by A1 is equal to 1. Okay, now this one I don't understand, but what I was trying to do was the following. Let's assume that we have a matrix which is 3 by 3, random number generators. And if we do here sum of AA, I mean, this is what I was trying to do. If you sum over twice, we get the summation of all this matrix which was here. So sum. And then looking at the images, by doing sum, I was trying to add up all the pixel intensity values which were seen in one layer, and I was trying to compare those, but maybe I made a mistake when I was writing down the A. This is the mistake, but I can correct this. A2 is a third layer, and A 1 is the first layer. A2 divided by A1, 0.1. So it's 10% less. So this means that the blue component is less. Anyway, so what we can do next is that these images, we can make this A black and white. This is RGB to gray of the original A. And then we make this variable double, evaluate selection. So here, okay, we should not have. So here we get the ABW, which is the black and white signal. It's still unsigned integer 8, but then we make it double. Why it's not double yet? Wait a second. Maybe we did not run this, evaluate selection. Oh, but we can take a shoot at rate. Okay, I forgot this. Then let's do it like this. Okay, so this variable, this became double, and a few of these figures, we can close them. They also suck up some good memory. And now that we have in double, all that remains is that in order to do the wavelet transform, so we can actually look at, let's copy paste this here, no? So we have this ABW, I think we are on this part, and then the next step we determine what are the NX and NY, which is the size of the image, which is 400 by 500. It's also obvious here, and these we need. So this says subplot imshow, okay. Now this is the wave deck decomposition. So all we need to do in the high-level programming languages is that we just need to apply this operator, which is wave deck. If it is a signal like the function S, which we observed here in the Gabor transform code, we just need to do wave deck. But if it is two-dimensional, we do wave deck 2. Then we get the coefficients S and C and S. So that's it. It's over. C and S, we got these results here. We can have a look at the. So C is composed of how many coefficients? So this is the number of coefficients is equal to the number of. So we have 400 by 500. This is the size of the image, and apparently we have 20,000 or 200,000 pixels. So 200,000 pixels, it corresponds to an output of coefficients of 200,000, which is this value C, which we can have a look at this value C, and they start from 56, 56, 55, and okay, we have some, the very first terms, they are something around 50. Let's have a look. We are well beyond few hundreds. Okay, they're still there. Oh, we even get 500. Okay. But we have 200,000. So if we move around here, we see some values which from an amplitude of few hundreds, like 300, 400, we have also amplitudes which are around 2. Here we have -6, 13.5, and here we start getting some zeros. Probably these are not, wait a second, this is C, 86,927. 86. It is 0. I was hoping to get maybe some epsilon. Some epsilon, I mean any number which is 10 to the power -16. But this is really being very discrete. So here we are full of zeros. So this region is empty. Here, this region is back again. Yes, there was a comment?
Deci ori vleri negative, si ka mund që vlera pikselesh ato. Si e ka vlerë negative?
Vlerë negative, po jo, këto janë vlerët negative të wavelet transformit. Pra C-ja dhe S-ja, wait a second, this is AB, this is the pixel intensity, ABW. Më kupton gjenti? Pra C-ja dhe S-ja janë wavelet transform. Dhe në qoftë se ka një vlerë negative, është sepse projekcioni në atë mod, the projection of that signal at the specific frequency or the specific mode is -1. It's like you are taking the projection of a vector in the Cartesian coordinate system. It would be in the second quadrant, and you get some small negative values, right?
Oh, great.
So this is one way to represent it, but those are the coefficients that come out from the wave decomposition. So, so dB, what did we use? Wait a second, we used dB1. I'm not sure if there is, I believe there is also dB2, which is Debesius. This is Debesius wavelet type 1. We can put here also, let me see. We can call this one 2, and we can make this type 2. Let me see if this is what I think it should be, evaluate selection. Okay, we got S22, and we notice that the S values, the Debesius filter of type 2, it produces different coefficients. And let's see how much different they could be. So we can do here C2, 1 to 5. I'm not sure if I can, if MATLAB allows this one. 1 to 5. Is it with a comma? Okay, no, it's something like this. I believe it's. Okay, so we subtract those, but wait a second. What is this? 1, 5. Okay, so this got the first row, fifth element. Okay, this is what is doing apparently. I wanted to subtract the very first components. Anyway, so this is apparently they are different. So the Debesius type 1 and Debesius type 2, they have a different. The coefficients are different, but it would be interesting to look at which one is a better filter if you want to modify some specific components. Now, so WaveDeck, this is what it does. If we want, actually, we can plot the coefficients. So we got this C. Maybe we can do it this way. We can say figure 3, figure 2. We can say plot C, or no, S. Plot S, because this is, no, which one is, wait a second. The coefficient is C. We should plot C. And we do hold on. I don't know if this is going to be very smart if we do hold on, because we can do here also grid on. And we can do also plot C2. So we plot two different Debesius filter components on top of each other. So it looks like the first one, I'm not sure which one is the first one. Probably the first one is blue. Because when we plot these graphs, the new one is written on top of the previous one, at least we don't see it. So this is how they look like. They do change a lot. I did not expect them to change this much. Let me see. Anyway. Yeah, there's a huge difference. And actually, the major difference is around here. So this specific wavelet, whatever it's called, we see that there are some regions where one of them is almost zero or almost negligible, small value, but the other one, it's non-zero. So it remains, is different from zero for more. So this looks like this is full of blue, representing the specific wavelet decomposition. And there is very much, a little less than the red color, which corresponds to the other wavelet decomposition. Okay, so these are the coefficients, which are way different from what we have seen in Fourier transform, for reasons that we said. Just that the coefficients are listed in the line from 1 to 200,000, equal to the number of data sets that we have. And what we can try then is that these values that we have, we can modify them a little. So, for example, we can, allow me if I can get this part of the code. This will simplify some of our work, and let's see what we get. We see that C. This B is equal to size of C2. This means that this is the second component of C. the same way that AAA can be random number integer generation, 3, 6, and here the size of AAA, the second component, this is showing us the number of columns, okay? This is what this is doing. So here the B is going to be equal to 60,000. Sorry, 200,000. Evaluate selection. Here we get the value of B. So, and then we can define so I'm going to say these components of X of the wavelet, which is from 1. So this is trying to define some values which are going to be used here when we modify the values of the coefficients of the wavelet decomposition. Let's go a little slowly to understand what we are doing. So let's see. We can set, if we look at this decomposition, these threshold values are the threshold values which are shown in the x-axis. By adjusting these threshold values, we can make 0 specific components. But let's have a look at the graph. Okay, so these threshold levels is, let's see. For example, if we have small values around here, what we can do is that also to decrease the computational complexity, there are some values which are epsilons. Epsilons, I mean something like 10 to the power 3, 10 to the power minus 5. What we can manually do is that we can zero out anything which is smaller, which is smaller than 50. So on the y-axis, we see here 200, 400, 600. Of course, we want these high components to be there, still there, but we might cut out some other components with a smaller amplitude. And to do that, here we can set some different threshold levels, like 50, 100, and 200. And this J is going to switch, pass through wait a second. This B, let's do it like this. And then this says that we're going to check, actually the image is huge, it's going to take some time, but apparently this is going to do the following. Any C22, so actually maybe I have to clear C2 because apparently it's a variable which is defined here. Let me do this, clear C2. How does clear work? Okay, we took it away. C2, we can even, okay, so because C itself, it was this coefficient that we saw that we were looking at the graph, and then this is this is going to scan all the values one by one, and is going to check if the absolute value of each of the values of C2, they are smaller than threshold, so if they are smaller than 50, which is assigned in line 19, then we manually set it equal to 0. And then in the end, we can determine a percentage which is, so count, in this case, what is count? Count is equal to the number of coefficients which are made 0, okay? So this would be the number of coefficients that are zeroed out. So, and then in the end, we can calculate a percentage which is defined as the number of coefficients that are zeroed out divided by the length of C2, because let's say 10% of the coefficients we make them 0, then we would get like 10% here, okay? So we're going to get the number of 0 divided by 200,000 times 100. Then in figure 2, we can plot, what is this, subplot? Okay, so we're going to plot four different graphs. It was going to be 4 by 1. And here we plot XW1, C2K. So here we're just trying to plot three different graphs for 3 different thresholds. This is what this is going to do. And we can try and see what we get. So if we run this section, okay, so these flowers that we had shown initially, this is figure 3, and these values here, wait a second, here the threshold was set to 50. Let me try to understand. The threshold here is 50, and here the threshold is, what was it? Let me see. 50, 100, and 200. So threshold initially, when j is equal to 1, because this is the j. Oh, okay, so we make 0. Okay, this makes sense. I believe we initially zero out the 50, and then the 100, and then the 200. But how can you see it here? So C2 are gone. In fact, this XW1, this is the x-axis, which means that we're just making some artificial x-axis for which we can plot C2 as a function of those, because this is any number from 1 to 200. So this is 0 to 1, apparently. So these graphs, they are 0 to 1. Yes, that's what they are. So this x-axis is changed from 0 to 1. And then here, we observe that we have made 0 anything smaller than 50. And we almost don't see those. So these large values, like above 50, 100, 200, they are still here. But later on, if we clear out anything smaller than, so actually we can have a look. From 0 to 5, so this is what we get. I believe we had another figure here. No? Maybe it's overwritten. Okay, maybe we close it to look at what the coefficients were. And actually, as a result, so what we do is that initially we had a good-looking image, and finally we can see that there is like GNP images. We can read what this is here. We can still read it here, but here when we take away coefficients that are larger than, smaller than 200, we cannot read exactly what is this writing here. And let's see what we have done. So this is one way to decompose a data set, in this case an image, into the various frequencies. And after we do this modification, what we do next is that we reconstruct the image, okay? So we have the C, this C, which has the coefficients which are shown here. We make them equal to C2 because we want to rename them only within the first for loop. So they become C2. C2 it's thresholded. After C2 is thresholded, here we reconstruct the values. So this C2 which is cut out or reconstructed or filtered out is used to make up the signal again. But when you make up again, you don't always reproduce the quality that we had initially. And the reason, I believe it's clear. So if we want to remove some noises, we can use this. But sometimes if we use a very, depending on the threshold that we can do, we can even damage the signal. Now, the wavelet decomposition, it is a very good technique that is often used in computer vision, in artificial intelligence, because it can, depending on the type of operation that one can do, one may need to use a specific wavelet to modify the signal in a specific way, which produces good outcome, results. So let's say, for example, you are in this space station and you want to count let's say, the debris that passes from some objects. If you use Fourier transform to filter out the data, it is observed that it's not always the best way. Okay, so we have a ground truth, and the images are processed when they do, let's say, the filtering, when they apply a specific operator. What happens is that when they compare the results with a specific ground truth, the wavelets, they seem to operate better. And again, these wavelets are not only used for images, it can be any type of data. So, for example, you can find in the literature, just, for example, a specific operator. What they do is just, they have a new data set, which could be very unique. And this data set, they could be, for example, let's call them microscopy images or images from microscopes. And when we process them, doing a wavelet decomposition could be more productive, or could the processed image could become much more easy to be analyzed. So yes, so we did the decomposition in line. Where was this? We did the wave deck in line 14, and this actually we had the S. Wait a second. Okay, I just changed the C2. Wait a second. Oh, okay. I see that. No, I think that we just changed it for a moment here. Maybe it's best if we turn this back where it was, because we just wanted to see the difference between the Abeshis 1 and the Abeshis 2. So this is all we did. And we noticed some difference between these filters. And actually we can run this whole again, just to see what we observe. Sorry, save. No. Don't save the workspace. Give it out. Editor. Okay. So again, we can start run section. So we get this value. Okay, we have a beautiful figure, and we have also the best components which can be easily distinguished when you do the decomposition and the reconstruction. Because initially the image we do wave decomposition, and then we do wave reconstruction. So this is the part of the image that we can keep track whether the resolution becomes worse or better. And then we continue this way. We run this section. Oh no, we plot on top of this. Okay, we didn't want to do that. But let's run the final part. Okay, actually, there is a problem why we don't see something useful. No, this is RGB2 gray. Okay, no. I don't know why we don't see it now. We saw it before a while. Okay, okay, same problem that Genti corrected me before a while. So here, I have here AVW2. Let me call it like this. Yeah. Okay, we have no errors. Now should be better. Okay, so these are the coefficients, and we were trying to simplify them. So this way, we are in fact, we can use this technique also to compress the image. The images, we can compress them by saving in this, by zeroing out some of the coefficients, but sometimes we are getting really bad, wait a second, really bad resolution because we cannot read specific information. Okay, so in fact, many properties that we see here that we can use the wavelets. I think there is a command of MATLAB which is wave menu, and other than wave menu, there is also something like filter something. So that 1D. So if you spend a couple of minutes just going over these toolboxes of the wave menu, you can experiment with them. And you can also you can import one of your own signals or data set that you might have gathered from wherever, and you can decompose it using the wavelets here. But I don't see. Okay, no. Okay, sorry. I have to load a signal, basic signals, sum of signs. Let's see. Okay, so we can, wait a second, we can load the signal, if we load it, okay, so if you have an image from somewhere, yeah, that's a good thing. So this toolbox, it will help you to include your own signal, import it here, and modify whichever way you want. So apparently this is wavelet Daubechius type 3. Apparently there's, oh, no, this is not type 3. This is, no, Daubechius. But what is this? This is level 5. So here we are using level 5 decomposition. Actually, yeah, this is how these Daubechius look like. So it's a wave, the first level, this is like sine of x. The second one is sine of 2x. Then we have sine of 3x, sine of cosinus, sinus 2x, 3x, 4x. Kështu është si ecën edhe valet e Daubechius që po diskutojmë ne. Dhe ky është sinjali fillestar, ky s-ja këtu. Dhe let's see here, analyze. Okay, so in this analysis, the projection of this signal into the lowest component or the lowest frequency of the wavelets, this is how they look like. Okay, so we see that here in the first section, which is from 0 to 100, maybe those are seconds, from 0 to 100, we see this feature, which is like a step function, which is positive, then it immediately drops because we have the drop of this sine function, right? So this is really good to mimic general representation. So I'm not sure whether you can see my mouse well. Then a little later, we see that the function increased and the projection of this signal in red is projected as this step function, which we can see it here. And then this is the first order wavelet decomposition. Then we have the second order, the third order. Then in the end, by adding up the signals of A5, D5, D4, D3, D2, adding all of these up, we can reconstruct the original signal. And some of these, we could, wait a second, we can change levels. Yeah, here we have less levels. If we decrease less levels to decompose a signal, then the task, which can be assigned to higher order frequencies, has to be done at the very first, at the very lowest order decomposition. So if you, let's compare this. You see now here, the decomposition, wait a second, no, we have D2, no, this is 2-level decomposition. This is 3-level decomposition, this is 4, yeah. And this is 5. You know, sometimes I forget the way that we operate. Whenever I need this, so let's see, decomposition level 5, S is equal to A5. Actually, it's written on the top of this. If you read this one, it's written in very small letters. Decomposition level 5, the original signal S is equal to A5 plus D5 plus all the rest of these terms. And if, yeah, this is how it is going to be. And, yeah. Okay, but whenever you need these, you could, so let's see, we have another Haar wavelet. The Haar wavelet is also a very classical wavelet. We have the same signal, but we are using the Haar wavelet at 5 different levels. Let's see here, 4 different levels. Okay, so that Daubechius, apparently they are all different Daubechius. So let's go back to this DB of type 1. This is DB type 1, analyze. This is what we get. Then we can get DB type 5. I mean, come on. This is, wow, this is almost a sine. Okay, this is getting closer and closer. Oh, okay. I didn't know, I never checked this in detail. I didn't know that the Daubechius at the high Daubechius type 10, apparently it's approaching to, what is it? This one, it seems like, is this a sine or a cosine? What do you think? The A4?
Deci vlera po Lukash 0 ta kontrash kosinus.
Ke drejtë Gendi, ke drejtë. Duket sikur është kosinus, po ama sikur ka një tentativë që do tulet ajo. Nëse po kjo është një argument I saktë në fakt. Duhet të shikojmë nëse ngjan sinus kosinusit, duhet të patë x baraz me 0 ku shkon ajo, se kujt I afrohet. Okej. Po interesant, në fakt Daubechius që shkoka ka që Wait a second. The batch is type 4. Is it what it is? No, type 1. Actually, I think we started with type 1. And yeah, type 1, this is what really is. Okay. Yeah. Okay, so these are some representations of. So we covered a little bit of the Fourier transform, which was actually we discussed a little bit, especially we saw the demonstration of how we can apply the short window Fourier transform with the signal that in the first part of the course. Then we also saw how the theory, just the very broad theoretical representation of how the wavelets can mimic or try to do a similar task like the short window Fourier transform. And now we just show how this one can be applied for images, where all we did it was this WaveDeck code. Now, this is all that we can do for today. And regarding this course, actually, from the first weeks, we have mentioned that in this course, we're going to have wavelet Fourier transform, wavelet transforms, advanced linear algebra, which will be the last part of the course, and also some some specific problems where you can, or all of us can analyze the computational complexity for some really nice problems. Now, next week, I hope we can have someone among you that I'm going to assign to talk about the complexity of specific problems, because from there I can also have the opportunity to assign you some homeworks from which I hope you are going to learn something. Okay, do you have any question for what we did so far? Any question? Okay. Okay, if you have no more questions, we can close. We can close for tonight. Let me see. There are a couple of you are presenting. Am I presenting my screen? Oh, yes, I am. Okay. Because I might have a few comments here. Okay, again. Is this? Oh, you're already there. Oh, okay. Thanks again. I thought this was written a while ago.
Thank you, Professor.
Yes, thank you to all of you for your attention. Edhe me të vërtetë do ju sugjeroj që këtë librin mund ta lexoni pak sepse është libër I shkruar shumë mirë, libër që përdorim si lëndë. Dhe besoj që do ju ndihmojë për shumë elementet për të cilët ne I trajtojmë te lënda jonë. Për javën që vjen, pasi kam menduar edhe diçka tjetër, te lënda jonë, pjesën e midtermit, se koha kalon edhe shpejt, pjesën e midtermit mund ta konvertojmë të gjithën në projekt. Dakor? Nuk e di nëse keni koment për këtë, po mund të çoni emailin nëse keni ndonjë shqetësim.
Në fakt, profesor, më mirë do ishte gjithë në projekt, them drejtën.
Gjithë në projekt.
Shumë, domethënë.
Dakor, mirë. Mund ta lëm projektin.
Për mendimin tim.
Do kërkojmë në javën e midtermit, ju do dorëzoni projektin, dakor? Për deri në javën e midtermit e kemi për detyrë gjithë bashkë që ta dorëzojmë atë pjesën e projektit, ose për në final do kemi projekt tjetër, dakor? Kështu mund ta lëm. Mirë atëherë, nëse kemi pyetje tjera, unë ju falenderoj për vëmendjen. Edhe takohemi herën tjetër. Natën e mirë, faleminderit edhe një herë.
Natën e mirë, faleminderit.
Nëse keni librin atë, mund të tregoni edhe autorët e atij libri, edhe Hersin me foto.
Çfarë tregoj keni librin?
Autor desha me kohë, Nathan Kutz.
Po, Nathan Kutz, po. Është syllabusi, it's in the syllabus where it is specified. It's really a very good professor. This you can follow his textbooks. It's a good one.
Faleminderit.
You're welcome. Faleminderit Gendi për komentet, faleminderit